All right, so for our one sample t-test, our goal here is going to be to use a t-distribution to help us evaluate a statement about what's going on in the population. So I'm starting out here by just drawing a t-distribution. So again, it's shaped like a normal distribution, especially for sample sizes that are greater than 30. So anything we're doing here, you could also do with a normal distribution. But typically, when you do a test like this, you use a t-distribution, so we're just going to start there. And our first step in performing a one-sample t-test is to write hypotheses. And our null hypothesis, we write out like this with HO. And if you remember back to the slide before, what we're testing is the statement that the true value for the preferred sentence for robbery in New Jersey is 15 years. So you could say all that, you could write it all out in words. So your null hypothesis would be that the true mean preferred sentence in New Jersey is 15 years. Or, which I'll do right here, you can write it out in the form of an equation where we would say that mu, or our population mean, is equal to 15. So in other words, in the population that we're looking at, which is the population of New Jersey, the preferred sentence length is equal to 15 years. Our alternative hypothesis, again, it's just the opposite of that. So we're saying if we reject this and we say, you know, it's really, really unlikely that this statement is true, what's the alternative? And in this case, the alternative would be, well, if it's not 15 years, then it's not 15 years. And so we would write that out as this equation here. So mu, or the population mean, is not equal to 15. And then you would say that in words as that the true population mean preferred sentence in New Jersey is not 15 years. What I'm also going to do here is just write out our sample information because we're going to be using this to perform the test. So in our sample mean, or x bar, is equal to 10.6 years. Our sample standard deviation, or S, is equal to 5.8 years. And our sample size, or N, is 100. Alright, so we've done our first step now, where we're not actually doing anything with the sample yet, we're just making some statements about what might or might not be true in the population. Our next step is going to be using the sample, though, and for that we're going to need to fill in some information about our sampling distribution. So your t-distribution here is a sampling distribution. And that means it gives us information about the probability of getting different sample values. And specifically, we're looking at sample means here. And the probability of getting each one. So this should look, at this point, pretty much exactly like a normal distribution. Again, the main difference between normal distributions and t-distributions is that t-distributions have different shapes for different sample sizes, and that's because instead of calculating them based on a population standard deviation, you calculate them based on a sample standard deviation right here. And that's just a star to highlight this. It doesn't mean anything. So we're now going to work on filling in some values in our t-distribution, which we're going to be using to perform this hypothesis test. So, like a normal distribution, t-distribution has an overall mean, which we can call mu, and it has a standard error. Unlike a normal distribution, though, our standard error is based on this sample standard deviation, so it's estimated rather than known. And we refer to the estimated standard error as an S sub x bar. So we've just got our S here. We're going to call it a big S sub x bar, and that's estimated standard error. And if you remember on a normal distribution, this would be your regular standard error. So what we have with estimated standard error is our best estimate for your standard error, which is the standard deviation of a sampling distribution. And it's our best estimate, and it's based off of this sample value. We also spent a little bit of time last week, although not too much, talking about how to calculate the estimated standard error. And you do that using the estimated standard error formula, which last week we just plugged directly into an equation for a confidence interval. This week we're going to be doing it in a separate step. And to calculate the estimated standard error, we're going to use an equation that looks exactly like our regular standard error equation, except that instead of having our population standard deviation here, we're going to be using our sample standard deviation. So to calculate the estimated standard error here, where, remember, this one would be sigma over the square root of n. Instead of doing that, since we don't actually know the standard deviation for preferred robbery sentence length in the population, we have to base it off our sample. So we're going to estimate the standard error of our sampling distribution using this equation here. So we have both of these values already. They both come from the sample. Our estimated our standard deviation, which we're going to use as part of our estimated standard error, is equal to 5.8. And our sample size here is 100. So we're going to take 5.8 over the square root of 100 to get our estimated standard error, which again is the equivalent to your regular standard error in a normal distribution. The only difference is that we are acknowledging that this one is just an estimate based on our sample, and it's not actually a known value. So that's why we call it S instead of sigma. So if you do this, you end up with 5.8 over 10, and that comes out to 0.58. So if you saw the DocCam video last week, and I learned that apparently that wasn't linked up right either, which is, again, why last week was a freebie. But if you saw that, this should look familiar as well, because this is part of what we calculated when we were using the same data to form a confidence interval. But we're going to be doing something slightly different with it this week, and now you can see kind of where it fits into the grand scheme of things. And specifically, this value is our standard error, or in other words, the standard deviation for this sampling distribution. And similar to a normal distribution, we know that our overall mean here is just going to be equal to our population mean, so we can fill this in as 15 as well. So what we have here is a sampling distribution that shows us the probability of getting different sample means if our null hypothesis is true. So in other words, if the true population mean really is 15, and we're going to say if it's 15, we're just going to call it 15 and put 15 right here. If the true population mean is 15, and we take samples of 100, and we estimate the standard error, this sampling distribution tells us the different sample means that we could get and the probability of getting each one. And you can read this like any other bell-shaped distribution, where sample means that are close to 15 would be more likely to get if our true population mean is 15, and sample means far away from 15 would be less likely to get if our true population mean is 15. So in other words, if our null hypothesis is true, we would be able to say that if we took a sample, it's likely that our sample mean would be near 15, and it's unlikely that our sample mean would be much higher or much lower. Okay, if the null hypothesis is true. And I'll write that up here too. If so that's what we're trying to describe with this graph here. That's saying if our null hypothesis is true, what are the different sample means we could get and how likely are they? And again, we're doing a t-distribution because we don't actually know the population standard deviation, and instead we're estimating it based on this, and we're using that to calculate the standard error for our sampling distribution for means using this estimated standard error equation here. All right, so we haven't actually gotten to the second step here. This is all part of the setup. And our second step is going to be to calculate a t-statistic. But hopefully what you can see here is that in doing this t-test, we're working with things that you've essentially all seen before. So we know how sampling distributions work. We know that they show us different sample means you can get and different values, and the different probabilities of getting those different sample mean values. You know what a standard error is. This equation should look pretty familiar to equations you've used before to calculate standard error. So we're all in familiar territory with this stuff. And we're going to stay in relatively familiar territory as we move forward. We're just going to be doing different things with it than we have before. All right, so what a test statistic is a statistic that shows you, on a standardized distribution, where a particular sample mean would fall. So, we had our sample mean here was 10.6. So if you were to plot a sample mean of 10.6 on this distribution here, 10.6 is less than 15, so it would be to the left of it along the x-axis. And you could just draw this here to show where our sample mean would land. So these are different possible sample means that you could have along the x-axis, and our actual sample mean that we took had a sample mean of 10.6. So we're saying, if the null hypothesis were true, we could plot our sample mean kind of like this here. We know it's less than what we would expect, and we could put it on the x-axis there. We could standardize everything and write this graph again. So just like with a standard normal distribution, you can standardize the t-distribution, and then everything stays the same, except that instead of having years as your units, we're now counting in t-statistics. So when we were working with the normal distribution, remember we would standardize our variables, and then instead of counting whatever we were counting in, then we were counting in z-scores. So it's like converting from feet to inches, and the only thing that changes are the units that you're using. It's the same thing here, except that here we're working with a standard t-distribution, and we've taken all of our numbers here that were in years before, and now we're counting in t-statistics. So it's shaped pretty much like a standard normal distribution at this point. The question that we have, though, is where does our sample land? And what we're working towards is trying to figure out if our sample is pretty likely, so if it's kind of in this big hump of values here, or if it's further out, like in these tails. And if it's one of the sample means that are more likely based on our sampling distribution, then we'd say we don't have a whole lot of evidence against the idea that this is actually what it looks like and this is what's going on in the population. If, on the other hand, our sample mean is way, way different than we'd expect, then we have evidence that, this isn't really the situation in the population. And so the closer our sample is to this mean that we're expecting, the less evidence we have to reject the null hypothesis. The further away our sample value is from this mean we're expecting, the more evidence we have. But to figure that out and to put numbers to it that give us actual probabilities about getting this sample, in a world where the null hypothesis is true, we're going to turn to the standard normal the standardized t-distribution here. And the idea is that, similar to with confidence intervals last week, and similar to what we did when we were just working with the standard normal distribution and the sampling distribution before, once it's standardized, we know the exact probability of getting values that are, or getting outcomes between different sets of values because it's the same graph every time, and then it's just a matter of looking up what those probabilities are. So if we can standardize this, in a nutshell, we can find out the exact probability of getting a sample value that's as extreme or more extreme than the one we actually got. And so we'd be looking at the area under the curve that's beyond our sample value. And what we do here is, because we haven't said whether we think our sample is going to be more or less than the sample mean, than the possible population mean, we actually look at it on both sides. So we say more extreme or less extreme, so if it's in, the very unlikely set of possible sample means on this side, or the very unlikely set of possible sample means on this side, then we would reject the null hypothesis. But I might be jumping the gun a little bit here. So the next thing that we're going to do is calculate the t-statistic that corresponds to our sample mean. And so a t-statistic is equivalent to a z-score, except that it's plotted on a t-distribution instead of a normal distribution. Otherwise, everything about it is the same. And the t-statistic is given by the t-statistic formula that looks like this. Also a tongue twister. And your t-statistic is calculated from this equation where you have your sample mean, your overall mean, sorry, this should be X bar here, and your estimated standard error. So this should also look pretty familiar. If you recall, a z-score was calculated using this equation. So the only thing that's different is that instead of having the actual standard error of the sampling distribution, now we have the estimated standard error, and we call it t instead of z. So what we're going to do is we're going to calculate a t-statistic that corresponds to our sample mean that will let us plot it on this standardized distribution. So it'll tell us how many standard errors away from the mean we are. And so we have all of these values already. So here we have our sample mean, which is 10.6. We have our sampling distribution mean, or overall mean, which is 15. And again, this value is just based on our null hypothesis. We're saying, if this is really what the situation is, we want to know what the sampling distribution looks like. So if the true mean is really 15, this is what the distribution looks like. So we're getting our overall mean from that statement of if this is true, this is what it looks like. So, same as this. We also have our standard error for the sampling distribution, which we just calculated in this step over here. And again, this is the standard error that's our best estimate based on the sample standard deviation. And we just calculated this to be 0.58. So we have all the ingredients that we need to find the t-statistic that corresponds to this sample value right here. So we can plug all this stuff in, and then we get t is equal to our sample mean, 10.6, minus our overall mean, which is 15, divided by 0.58. And if you do this math here, it should come out to negative 7.59. So that means that on this standardized distribution that we drew, our sample value is negative 7.59 standard errors away from the mean in a negative direction. So it's got that same interpretation as a z-score as well. So we're saying that in our t-distribution here, this sample value of 10.6, because same graph, is 7.95 standard errors away from the mean going in this direction. So your second step there is calculating the t-statistic. But now we're going to talk about what exactly we do with that. And so let's get back to this idea of, what is a likely or an unlikely sample mean if the null hypothesis is true. So here again is our t-distribution in a world where the null hypothesis is true. And this is the not standardized version. Also not drawn to scale. So here is our sampling distribution if the null hypothesis is true. If, on average, people really want a sentence length of 15 years for robbery, your most likely sample mean is 15. It's unlikely you're going to get a sample mean that's much higher. It's unlikely that you're going to get a sample mean that's much lower. And in this case, I'm now going to actually just shade the areas that we're going to call unlikely. And we'll say that the whole area in the middle is pretty likely. Our goal in hypothesis testing, and the reason that we just did everything we did, is we're trying to figure out if our sample mean falls in this unlikely zone, or if it falls in the pretty likely zone. And we don't actually know, based on what we've done so far, which zone we're in. And what we're going to figure out is, based on our test statistic that tells us, where on the sampling distribution our sample mean falls, is it in this zone where we say this is a really unlikely sample mean to get if the null hypothesis is true, or is it in this zone where we say this is a pretty likely sample mean to get if it's true? And if we say that our sample mean is in this unlikely zone, we would reject the null hypothesis. If, on the other hand, the sample mean is in this middle zone of pretty likely sample means that you could get if the null hypothesis were true, we would fail to reject the null hypothesis. It's in that pretty likely zone. So if the sample is in one of these tails that's shaded off, we're saying this is just too unlikely if the null hypothesis is true. Then we're going to say our sample gives us evidence that the null hypothesis is not really true. That the true mean value is not really 15 if our sample is so low that it's in this teeny tiny tail that we have out here. On the other hand, if our sample mean of 10.6 is in this zone here that's among the values that you're likely to get with a true population mean of 15, then we would say we fail to reject the null hypothesis. And it's a sample mean that we would expect to get if the true population mean were equal to 15. So if our null hypothesis were true. And then as a reminder, you never say that you accept the null hypothesis. The language is that you always either that you reject it or you fail to reject it. And that language reflects what's going on here, where here we have evidence that your null hypothesis is unlikely. Your sample mean probably wouldn't have come from a population where the true mean was 15. So you're rejecting the idea that it's 15. Here, the only thing that we can say is that, we don't have any evidence that it's not 15. But we also don't have any evidence that it particularly is 15 either. So this sample mean that you could get with a lot of different true population means. The only thing that we're saying here is that, we don't have any reason to, totally throw out the idea that it's 15. how much of the graph is shaded is based on your alpha level. So your alpha level, as I mentioned before, gives you a threshold for deciding when to reject the null hypothesis. The way that it does this is by telling you how much of the tails of the graph we're going to call the unlikely zone. And when you have an alpha level that's relatively high, and this is for illustration, not really drawn to scale, if you have an alpha level that's relatively large, like 0.05, which also happens to be the most common alpha level in criminal justice and other social science work, then you're having a relatively large area in the tails shaded, where you'd say you reject the null hypothesis if your sample mean falls into that zone, and you would fail to reject the null hypothesis if it falls into the middle zone. With an alpha level of 0.1, you have less of the tails shaded, where now you have a smaller zone in which you would reject the null hypothesis, and a larger zone in which you would fail to reject it. And then finally, if you have a really small alpha level, like 0.001, you're saying that your sample mean has to be in the teeny tiniest little corners of your distribution in order for you to reject the null hypothesis. So you're only going to reject if your sample mean is in these very, very small areas under the curve that are really far away from your possible population mean. Where you would reject the null hypothesis if your sample is one of these really, really unlikely samples, and you would fail to reject your null hypothesis as long as your sample mean is in this unshaded area. So just to recap again here, when you're looking at the alpha level, this is something that is chosen by the researcher, so the person who's doing the hypothesis test, and it's really based on whatever the purposes of the research or the hypothesis test are. A test like this is likely to cause you to reject the null hypothesis because it's relatively likely that your sample mean is going to end up in the reject zone even if your null hypothesis is true. So even if the true sample mean were 15, you might still get a sample mean that's in this shaded zone just by chance. On the other hand, if you're looking at a low alpha level, if your true population mean is 15, you'd need to have a sample mean that was really far away from it in order to reject that. If you're testing whether the true population mean is 15, you'd need to have a sample that's really far away from it to reject it. And so the downside to a low alpha level is that you end up with false positives, essentially, where you reject the null hypothesis by mistake. And you find evidence against the null hypothesis when really the null hypothesis is true. The downside to a very small alpha level is that it's a lot harder to reject the null hypothesis, and so sometimes you'll fail to reject it even when you should. So in reality, the null hypothesis wouldn't be true, but your sample isn't quite in this teeny tiniest zone of rejection, so you would fail to reject it. And so in this one, your total shaded area is 5% for an alpha level of 0.05. Your total shaded area is 1% for your alpha level of 0.01, and your total shaded area is 0.1% for your alpha level of 0.001. So hopefully this is sort of filling in the cracks a little bit in what I talked about in the slides, and where these things come from and how they connect to what we've done in the class so far. As a quick note, these t-tests that we're talking about are what are called two-tailed because we're willing to reject sample means that fall into the unlikely zone on either side of the mean. So if we got a sample mean that was a lot higher than 15 or a sample mean that was a lot lower than 15, we would reject the null hypothesis. There are also versions of this test that are considered one-tailed, where your rejection zone would only be on one side of the graph. And we're not going to go through how to do that in this class, but if you ever see something talking about a one-tailed test, it means that your zone where you would reject the null hypothesis is only on one side. So in this example, you're only rejecting the null hypothesis if your mean is higher than what you expect. You're only rejecting the null hypothesis in this other example if your mean is lower than you'd expect. All right, so that was a quick detour into what some of these terms mean as applied to the t-distribution specifically. Now we're going to come back to what we started here. So where we got before was coming up with this t-distribution for our specific hypotheses that we're looking at. So where we're considering whether the true population mean might be 15 years based on our sample of 10.6. We also have a test statistic, or a t-statistic in this case, for our sample mean. So we know that our sample mean has a test statistic of negative 7.95. The question we're going to answer now is whether that test statistic falls into the unlikely zone or the likely zone. And we're going to be able to do that using the standard normal distribution because it gives us information about the probabilities of getting values, that are at different points along the x-axis. More paper. And to determine whether our test statistic falls into the likely or unlikely zone, we're going to use something called a p-value. So I'm drawing out the standard t-distribution again. So this is our t-distribution with everything standardized. So we have a mean of 0 and a standard error of 1. And we're also going to now pick an alpha level for our test. So normally this is something that you would do at the beginning of the test, but you can also consider whether your null hypothesis would be rejected at different alpha levels as well. But we're going to say now that we're working with an alpha level of 0.05. So we're going to use our most standard alpha level in criminal justice and other social science research. This means that we're going to reject our null hypothesis if our sample statistic lands in the 5% of least likely sample means that you could get. So in other words, if our sample mean of 10.6 is one of the 5% of least likely possible values that you could get along the x-axis. But because we've converted everything to t-scores, we're going to be considering whether our sample t-score is in the 5% of least likely t-scores. So our total shaded area is 5%, and we want to know if our t-statistic lands us in that area. So does a t-score of negative 7.59 put us in this area, or does it put us in this area here? And we don't know yet. We're going to be answering that question by calculating something called a p-value. And what a p-value does is start with your t-statistic. So we have a t-statistic of negative 7.59 on our standard distribution here. And so this is x bar, and this lands at 7.59. So we're 7.59 standard errors away from the mean going in a negative direction. Because this is a sampling distribution, we can use the area under the curve to find the probability of getting a value that is as extreme as this sample mean or more extreme. So in other words, a value that's at this point on the graph or less. And because we're interested in whether it's as extreme or more extreme, we're actually going to look at the probability of getting one that's less than 7.59 or more than 7.59. So in other words, what's the probability of getting a t-statistic that's more extreme than 7.59 on either side? And the probability that we find here is going to tell us the probability of getting a sample that's as extreme or more extreme than the one we actually got. If the null hypothesis is true. So just to say again what I wrote out here, we're going to be using this standard t-distribution here to find the probability of getting a t-statistic that's more extreme than 7.59 on either side. And we're going to be able to do this using the area under the curve because this thing is standardized. All the possible areas under the curve for every t-statistic have already been calculated by other people. The probability of getting a t-statistic that's more extreme than 7.59, so that's less than negative 7.59 or more than 7.59, is equal to the probability of getting a sample mean that's as extreme or more extreme than 10.6 years if the null hypothesis were true. And because we're looking at minus 7.59 and 7.59 in this two-tailed test, we would be, looking at both sides of the graph on our not standardized version as well. The takeaway from this here is that we use the test statistic to find the area under the curve, and the area under the curve gives us some probability of getting a value that is either less than t equals negative 7.59 or more than t equals negative 7.59. And that area under the curve is your p-value. So your p-value is the probability of getting a sample mean as extreme or more extreme than the one you got. if the null hypothesis is true. Because remember, this whole graph that we have here is based on this starting idea that the null hypothesis is true and the true population mean is 15. So that was our starting point. So everything else we're doing is conditional on this null hypothesis being true. So with that in mind, once we calculate the test statistic, we can find the probability of getting a sample mean that is as extreme or more extreme than the one we got in this world where the null hypothesis is true. The final piece to the puzzle is that if the probability we come up with for our p-value is smaller than our alpha level, we're going to reject the null hypothesis. The idea here being that if our alpha level is 0.05 and we have our 5% of least likely values here, if our p-value is smaller, it means that our probability is all contained within the values shaded off by the alpha level. If, on the other hand, our p-value is larger than our alpha level, then our p-value is outside of the shaded area, and it includes some of the values that would be in the don't reject zone. So if your p-value is smaller than your alpha level, you know that your probabilities and the areas under the curve is all inside of this zone where you would reject the null hypothesis. And your sample mean is beyond that threshold that we've cordoned off as being your too unlikely to come from a world where the null hypothesis is true values. If your p-value is larger than your alpha level, it means that the test statistic you got is in this zone where you would not reject the null hypothesis. And it's not that unlikely to get a sample mean as extreme or more extreme than the one that you got. In this class, and in pretty much any application in life, you will not calculate the p-value by hand. And instead, the p-value is going to be calculated by a computer based on this standard distribution here. So you have a standard distribution, and based on whatever your t-value is, or your t-statistic is, you can just calculate that area under the curve using some sort of computer program. So in this class, what I'm going to give you is the p-value itself. And in particular, based on a t-statistic of negative 7.59, your p-value is less than 0.001. So something that you will see as we go through this class, and I come up with these numbers and then I actually run the program, so these are the p-values that correspond to the t-statistics. This one would be very, very small. And when it's small enough, the computer doesn't bother telling you what number comes after all the zeros. It just says that it's less than 0.001, or something similar to that. So what this p-value means is that there is less than a 0.01% chance we would have gotten a sample mean as extreme or more extreme than 10.6 years if the null hypothesis were true. In other words, our p-value of less than 0.001 tells us that if our reject zone is here and includes, you know, the 5% of least likely possible sample means you could get, our sample mean is really small. And it's, in fact, in the less than 0.1% of least likely sample means that you could get. With the t-value that's negative 7.59, it's way past that threshold where we would reject the null hypothesis. So we would say that because p is less than our alpha level, we reject the null hypothesis. Based on our sample mean of 10.6 years, we can say that we have evidence that the true population mean is probably not 15 years, because it's really unlikely. In fact, there is a 0.01% chance that we would have gotten a sample mean that was as extreme or more extreme than 10.6 years if the true population mean were 15 years. Where again, extreme means as small or large. So we wouldn't have gotten a sample mean that was as far away from 15 on either side, you know, if the true population mean were 15. It's so unlikely, it's way past our threshold for rejecting the null hypothesis, so we are going to reject the null hypothesis. Another way of saying this is that the difference between the sample mean we got and the population mean we were expecting is statistically significant. And so you see the term statistically significant all over the place, and this is what it actually means. It refers to whether or not you're rejecting the null hypothesis based on some alpha level that has been set beforehand. So it doesn't necessarily mean that it's important or anything. You know, sometimes it will be, sometimes it won't be. But what it means is that based on a formal hypothesis test, you have rejected the null hypothesis, and the difference between your sample value and the population value that you were considering as a null hypothesis is big enough that you reject the null hypothesis. Alright, so as I warned you guys before, the first example was going to include a whole bunch more explanation and describing what all this stuff means and how it fits in with the other things we've learned in this class. I can honestly say that I took different versions of Intro to Statistics, I want to say 4 separate times in my life, different majors like college, grad school, and it probably wasn't until I started teaching this class that I fully understood what was going on here. So if it's taking a little while to sink in, that's perfectly fine. But what I will do now is show you how to do one of these hypothesis tests, how to interpret the results, and do it much more quickly and without all of this extra explanation about, you know, what's going on with the sampling distribution and what zone we're in, and so on. So I'm going to go through one last quick example here for you guys that will hopefully help with the problem set as well. And I'm just going to go straight to a separate piece of paper. Alright, so for our next example here, we're going to shift gears a little bit. And we're going to go through an example where we're going to say we want to evaluate a statement made by a prison warden about how many hours of visitation the inmates or people in the prison are getting per month. So the claim is that inmates get, no, I'll do a different number here, 20 hours of visitation per month on average. So this is a statement about something that might be true in the world, and we're going to use evidence to try to determine, how likely it is that that's actually the case. So we're going to use a sample of 40 inmates. So that's our N, our sample size. We're going to say that we take a sample that comes up with a mean of 17.2 hours, which is our X bar, and has a standard deviation of 4.9. And we're going to say, before we start, that we're going to use an alpha level of 0.01 here. So this is a stricter test. That means that if we reject the null hypothesis, we have pretty strong evidence, that the warden's claim is not true here. And the fun part of this one is that I'm going to be going through these numbers as I do this with you. So I'll be putting them into my calculator, whatever you do with numbers in a calculator. And I'll be finding out with you whether we actually reject the null hypothesis here. So our first step is to write hypotheses. And we're always going to write a null and an alternative hypothesis. The null hypothesis is the one that you're going to be testing with your hypothesis test. So it's some claim about the world, and we want to see whether it's likely to be true based on information from a sample. So our null hypothesis here is that overall, in the population, so people who are in this prison, the average number of hours of visitation, so the population mean, is equal to 20. And so another way you could write this would be the null hypothesis is that the true mean number of visitation hours is 20. The alternative hypothesis is, again, just going to be the exact opposite of your null hypothesis, and it's what would be true about the world if you were to reject the null hypothesis. And in this case, if it's not 20, well, it's not 20. So our alternative hypothesis is that the true population mean is not equal to 20. And we could also write that, this is not division, this is just like saying a different way of doing it. We could also say the true mean number of visitation hours in the population is not 20. Okay, so that's step one. So step two is to find a test statistic. And for a one sample t-test, you're looking for a t statistic. And if you remember what this t statistic is, I can't say the words t statistic without tripping over myself. But what this t statistic is going to tell you is that I'll just start from the beginning there. So what this t-statistic is going to tell you is the probability of getting a sample mean as extreme or more extreme than the one we got here, which is 7.2, if the true number of hours of visitation per month is 20, as the warden is claiming. We calculate the t-statistic using this equation here. Where x bar is your sample mean, mu of x bar is the sampling distribution mean, and s sub x bar is the sampling distribution standard error, which we calculate using this equation here. So I'll calculate this one right now. So the first thing we're going to do is get our estimated standard error. And we're going to plug in our sample standard deviation, which is 4.9, and divide it by the square root of 40. If you do this, you come up with a value of 0.77. So the standard error for our sampling distribution is 0.77. Now we can plug everything we got into our test statistic equation and get our t-statistic. So we have a sample mean of 17.2. We're subtracting our sampling distribution mean, which is 20, so it's what we're getting from our null hypothesis. And we're dividing by our standard error, where the standard error is what we just calculated. Plug all this stuff in, which I'm doing now. And you should get a t-statistic of negative 3.64 when you round. So this tells us that on a standard t-distribution, our sample mean is at negative 3.64, where these are t-statistics here. And now the question we have to answer is whether this t-statistic lands in the zone where we would reject the null hypothesis, or whether it lands in the zone where we would fail to reject the null hypothesis. Here's where we turn to a computer and we ask it what the probability of getting this t-statistic would be. So with these values that we have here, and bear with me for a second, we get a p-value of 0.0009. So with a sample mean of 17.2, a hypothetical mean, so a mean of the sampling distribution of 20, and a standard error that we just calculated, that's 0.77. We get a p-value of 0.00009 for our test statistic that we have here. What this means is that if the null hypothesis were true, so if the true number of hours that people in the prison got visitation was 20 hours per month, we would only see a sample mean that was as different from that as 17.2, 0.09% of the time. as extreme or more extreme as 17.2 hours, 0.09% of the time. So in other words, if people in this prison were really being visited 20 hours per month, as the warden is claiming, it's really, really unlikely we would have gotten a sample mean as low as 17.2 hours in our sample of people. So with step 3 here, we're now going to evaluate whether our sample mean is unlikely enough to reject the null hypothesis. And you'll remember that we reject the null hypothesis when p is less than our alpha value. In this case, our p-value is 0.0009, and our alpha value is 0.05. So our p-value here is less than our alpha value, and we would say that we reject the null hypothesis. In other words, we have found evidence against the warden's statement that people are getting 20 hours of visitation per month in this prison. We could also now draw this out, now that we know what's going on here, by saying that if this is our zone where we are rejecting the null hypothesis, our sample mean is definitely in this rejection zone here. So it's one of the less likely sample means that you would get if the true population mean were equal to 20. Right. And that's it. So when it comes to actually doing the hypothesis test, as you can see, it's much less involved than when I went through when I was explaining each piece of it. So the key parts in actually performing it are writing out your hypotheses, finding your test statistic, which will then give you a p-value. And for anything we do in this class, I'll just give you the p-value. You don't have to find the calculator and plug it in yourself on the line. And then based on that p-value, decide whether to reject the null hypothesis. And we reject when p is less than alpha, which is the case here. Alright, so this was something of a long lecture between this one and the other one. I guess we're fitting in like, a week's worth of regular classes doing this, which I always forget once I get to this point, and I've been talking forever. So I'm going to shut up now. I'll leave you guys to go through the problem set. If you see any issues with the problem sets or anything else, please let me know. I hate giving you more problems in your life because of, my problems with technology. So give me a heads up if you see anything. Otherwise, reach out if you have any questions, and I hope you have a great week.